Hello, geometry folks, or algebra 2 folks, sorry. I hope you are doing well. Today we are going to talk about operations with radicals. Now, what you have really shown success in is simplifying radicals and rational exponents. So you guys have done really great in those. Now we're going to look at it, what happens when we have more than one term. What we've been dealing with so far is just one singular term, and now we're going to move on to maybe more than one term. So let's look at some examples here, just talking about operations with radicals. And I'm going to write this note down. When adding or subtracting radicals, you have to follow the like terms rule. For example, if I have a root 2 plus 3 root 2, I can go ahead and conduct this operation because I have like terms. So think about your radicals as like terms. We'll call them like radicals, which that's the vocabulary that we reviewed last class. But we can go ahead and follow this operation. So think of this, remember, as a 1. And so this will be 4 times the square root of 2, okay? If I don't have like rules, then this is completely simplified just like this. I cannot conduct this operation because I do not have like terms. When multiplying or dividing, and we've done these already because it's in one term, then we don't have to follow the like terms rule. We'll use the adding or subtracting of exponents, right? That's our product or quotient. And we've reviewed that many, many times. So if I have root 2 times root 2, I'm just going to multiply. Go ahead and multiply those numbers inside, or think about it as adding your exponents, right? Root 2 squared. In this case, it would be 2, right? Okay, so let's do some of these examples from your notes now that we have those two rules written down. So remember, when adding or subtracting radicals, we have two different terms here, right? We can follow the like terms rule, making sure that our radicals are like terms. All right. So let's do this one. The cubed root of 4 times the cubed root of 12. So the cubed root of 4 times cubed root of 12, we're multiplying here, so we don't have to follow that like terms rule, do we? So I can just multiply straight across here. So I can say, okay, this is the cubed root. However, yeah, you have to make sure that those are like. 4 times 12 is 48, and now I'm going to see if I can find a cubed root that's in here. So thinking about the cubed root, I know it's 16. Is that 16 and 3? The cubed root of 16 times 3. I'm going to check my math. 48 divided by 16. Yeah, 3. All right. No, it's 8, isn't it? That's a cubed root is 8. 8 and 6. Duh. All right, so the cubed root of 8 is 2 times the cubed root of 6. So we'll just simplify from there. So when you're multiplying, remember, your roots need to be the same, right? But you can multiply straight across if your bases are not the same. All right, let's try the next one. This is root 5 times 2 plus root 3. Now I cannot add these in the parentheses because they are not like terms. I would need to have a root 3 next to this one for it to be a like term. Okay, but I will follow my distributing property by multiplying the root 5 to each term inside the parentheses. So I'll have a 2 root 5 here plus, when they're inside, I can multiply them as long as they have the same root, and root 15 here. I don't have a perfect square in my root 15, so I can't pull anything out. They're not like terms, so I cannot add them. This is your evaluation of your operation there. All right, let's look at that letter C. I have 4 plus 2 root 5 times 3 minus 4 root 5. And we're going to distribute just like we did up here, right? When we distribute and multiply binomials, we multiply both by the first term and both by the second term, right? So I have 4 times 3 is 12. 4 times negative 4 is negative 16 root 5. So notice when they're not in the radical, I can multiply. When they're inside the radical, I can multiply, but not intermixing. All right, then 2 and 3 is 6 root 5, and 2 and negative 4 is negative 8 root. Multiply those together, 25, or 5 squared, however you want to write it. All right, so I'm going to look at my, remember when we did this in algebra with your x's and your x squared, same thing, same thing. So I have 12. I'm going to put those together because they're like terms. So I have negative 16 and 6 is negative 10 root 5. And look here, I can simplify this. Let's make that an extra step. You don't have to make it an extra step, but I will. All right, so I know that the square root of 25 is 5. So whatever, if I pull something out, I have to multiply it by this number. So if it's 8 times 5, because square root of 25 is 5, then my answer here is 12 minus 10 root 5 minus 40. All right, so what that left us with is 2 like terms here. I have 2 constants, so I can go ahead and put those together. So I have 12 minus 40 is negative 28 minus 10 root 5. My mental math is off today, I think. And so that's my answer. I'm completely simplified. I've simplified my radical. I've combined my like radicals, and now I'm done. Okay. That was letter C. All right, let's move on to D. I'll let you do D. Let's move on to E, because I don't want to run out of time here. Negative 2y plus the square root of 12y cubed divided by 8y. So I'm thinking here, man, it'd be really nice to reduce this, right? But I can't reduce it because I have this plus sign here. I have 2 terms. So if I were to reduce this using the 8, I would have to reduce this one as well. So I can't do that until I can figure out something here. So let's see. It's square root, and I have a y cubed. So let's break this apart into perfect squares. So I know that 12 is the same as 4 times 3, that's a perfect square, times y squared times y. So I'm going to pull out my perfect squares. Make sure I write my whole problem down. So I have negative 2y plus, pulling out a 2, pulling out a y, and what stays inside? They didn't have partners, they had to stay inside, is 3y, divided by 8y. All right. So because we're dividing here and because both of them can be simplified at the same time, I can go ahead and simplify both, right? So you can also think about it like this. It's just like typical fractions. 3y. So same thing, right? They have the same denominator. So I can reduce here. So if I reduce this one, I have a negative, just 1 on the top, right? Plus, here I also have a 1, and then I have that 3y. And divided by, when I reduce that, I got a 4. If they're not the same, this just so happened that both of them were, not a y, both of them were dividing by 2. So that means I can write them again like this. If you reduced them and they didn't have the same denominator, then you would leave them as 2 separate fractions, okay? That one was a little bit tricky. You don't have to write a 1 there. It's understood. But you do have to write a 1 there. Okay, let's talk a little bit about conjugates. we talked about conjugates last time being the opposite terms, right? So conjugates of A plus B, the conjugate would be A minus B. Pretty simple, right? If I have 2 plus root 5, the conjugate would be 2 minus root 5. If I have root 7 minus root 6, the conjugate would be root 7 plus root 6. So all we're doing is changing that inside term. And the goal here in changing that inside term is to rationalize your denominator. So we're doing this for a purpose, and that purpose is so we can rationalize our denominator. So the last one, root x minus 4, the conjugate of that would be root x plus 4. So the purpose, I know sometimes we always need a purpose for something, right? The purpose is to rationalize. Like we talked about last time in some of the ones that we did, it's that math rule that if we have a radical in the denominator, then it's an irrational number, right? So we need to make sure that we have rational numbers across, and in order to do that, we have to rationalize our denominator. So let's look at what happens when we multiply conjugates together. What happens? And I think this is the question on your notes. So what happens when you multiply conjugates together? So here's our f. It's square root of 6 plus 10 times square root of 6 minus 10. We're going to FOIL, right, or multiply binomials. So first term gets multiplied to both the last terms, second term gets multiplied by both. All right, so square root 6 is square root 36. Square root 6 and negative 10 is negative 10 root 6. Positive 10 and root 6 is positive 10 root 6. Are you seeing it already? Positive 10 and negative 10 is negative 100. So what happens when we combine our like terms here? Look at that, one's positive, one's negative. Yeah, and then our square root of 36 is 6 minus 100. So 6 minus 100 is negative 94. So your answer there would be a negative 94. We're going to practice this when rationalizing denominators. I'll show you how to work that. So think about this also. Remember, you talked about this in algebra. They're called perfect square. No. They're called opposite. I'm going to have the difference of two squares. Thank you. Oh my gosh. Difference of two squares. Remember when you talked about that? It's kind of like that, where when you multiply them together, the middle term is eliminated. So it's kind of like that when we're rationalizing. All right, when you have conjugates. You probably learned that word in Algebra 1. You didn't even know it. You didn't even know you'd be using it again. All right, let's move on to H, because we're going to be using our conjugates here to rationalize the denominator. So remember, in rationalizing the denominator, you want to multiply the term or the fraction by a form of 1 without changing the value of the fraction. And so the only way that I can change the number without changing its value is multiplying it by 1. That's the multiplicative identity property, right? How do I make it the same without making it the same? Well, I'm going to multiply it by its conjugate. But not just the bottom, because if I multiply it by the bottom, that's not a form of 1, right? I can only multiply it by a form of 1 if I have same numbers, right? Same number on top of same number, that equals 1. So think about that. Anytime you rationalize a denominator, you want to multiply it by a form of 1. So that means whatever you do on the top, you got to do on the bottom. All right, let's multiply straight across here. So I'm going to distribute my 2. So I have 6 minus 2 root 7. And in the denominator, we're going to multiply our binomials. So first number gets multiplied by both, second number gets multiplied by both. 3 and 3 is 9. 3 times negative root 7 is 3 times negative 3 times the root of 7. Positive root 7 times 3 is plus 3 times root 7. And then 7 and 7, that's negative root 49. Okay, let's simplify this. My numerator, I'm going to just keep there for a little bit while I figure out what's going on in the denominator. Look at that. My like terms here, my like radicals are opposite, so they cancel. And I have a negative 49. Square root of 49 is 7. So I have 9 minus 7. I'm taking this sign, right? This sign in front of it. 9 minus 7 is 2. So I have 6 minus 2 root 7 divided by 2. And now I can simplify, right? I can divide both of those by 2. Remember, you can only do it if it applies to both. Otherwise, you have to separate them out and make them two different fractions. All right, so 6 divided by 2 is 3, and 2 divided by 2 is 1. So what happens is it looks very different, although it is the same number. It just looks different. It's the same value. If I plugged this 2 divided by 3 plus square root of 7 and 3 minus 1 root 7 in the calculator, I should get the same answer, right? I should get the same decimal answer. Well, this one would be irrational, but we're trying to make it rational. Okay, let's move on. Let's try one more. Okay, so we have, let's move on to letter K. I'm going to leave those two in the middle for you to do and try. So I have a root x minus 5 divided by 2 root x minus 1. Okay, so I'm going to try to rationalize my denominator here by finding the conjugate, by multiplying it by a form of 1 without changing the value. So I have 2 root x minus 1, 2 root x, and 1. And my conjugate here, remember, is the opposite value. So it's going to be plus 1 on both. Okay, this is going to be a lot of work because on the top, it's not just one number, one term. It's actually multiplying the binomials, right? So first term gets multiplied to both. Second term gets multiplied to both. Let's do that first. X and 2 root x is 2 times the square root of x squared. X, square root of x times 1 is square root x. Negative 5 times 2 root x is negative 10 root x. Negative 5 times 1 is negative 5. Ooh, that's long, right? I'm going to leave that there because I'm going to do the bottom next. First term gets multiplied to both. Second term gets multiplied to both. 2x and 2x. 4 times the square root of x squared. 2 root x times 1 is 2 root x. Negative 1 and 2x is minus 2 root x. Negative 1 and positive 1 is negative 1. All right, let's see if we can combine some things here. Let's look at my numerator first. Let's work on that first. I know that the square root of x squared is just x, so I'm going to pull that out, 2x, right? Now I'm going to look at my like terms. I have a positive x and a negative 10x, so think about that as 1, right? Plus 1, negative 10, that gets me negative 9x. I can do that because they are like radicals, right? Remember that. And I have a minus 5. In the denominator, same thing as the numerator, this x, square root of x squared is just x. So I have a 4 times x. This is great. This is what we wanted our conjugates to do, is to cancel that out. And I have a negative 1. I'm looking at it to see if I can do anything in simplifying, and it looks like it's probably not going to happen. So I'm just going to leave it like this, and that looks pretty good. Same value, just looks different, right? Okay, last little section, we're going to evaluate the function. And when we say evaluate, remember that's just a fancy word for plug in, right? Or substitute. So if I have f of x equals x squared minus 2x minus 1, and I want to evaluate for f of 1 plus square root of 2, what that means is I'm just going to take this 1 plus square root of 2, and everywhere I see an x, I'm going to plug in that value, right? So here I have f of 1 plus square root of 2 equals 1 plus square root of 2 squared. It's just the x, so we have to leave the square root there. Minus 2 times 1 plus root 2 minus 1. So this one, since it's squared, that's not just squaring both terms. We can only do that when we're multiplying or dividing, right? Because we have both terms, that means it's going to end up being multiplying binomials. So it's 1 plus square root 2 times 1 plus square root 2 here. Minus 2 times 1 plus root 2 minus 1. You don't have to do this many steps. I like to draw it out sometimes, especially when we're doing it our first time. Okay, so multiplying binomials, FOIL, or first term gets multiplied to both, second term gets multiplied to both. 1 times 1 is 1. 1 times square root of 2 is square root 2. Square root 2 times 1 is square root 2. And square root 2 times square root 2 is square root 4. I'm going to keep going. I'm going to multiply here too. Don't forget your negative. Negative 2 times 1 is negative 2. Negative 2 times square root 2 is negative 2 root 2 minus 1. All right. Now I have it all written out. I think that I can probably combine some like radicals here. And I can. That's a square root 2. That's a square root 2. So I have a 1. Let's look at all my square root 2's. I have 1, 2. I have 2. And then minus 2. Well, those cancel, don't they? So that's a nothing. Square root 4 is 2 minus 2 minus 1. Okay, well, that's pretty simple. 1 plus 2 is 3. 3 minus 2 is 1. 1 minus 1 is 0. Okay, how do we end up with that? That's pretty cool. Okay, here we go. So f of 1 plus root 2 is 0. I would like to plug that into our Desmos graph to see if that matches. I'll have to do that during our class to show us how that works. Okay, let's do one more example, and then I'm going to let you do the last one. Okay. So we're still evaluating, but now we have a different function. We have our function g of x equals x squared minus 4x plus 1. And our evaluation is g of 1 plus root 5. Sorry, can't see that. So everywhere I see an x value, I'm going to plug in this 1 plus root 5, right? So I have g of 1 plus root 5 equals, plug it in here, 1 plus root 5. This is squaring, same thing like last time, minus 4 times 1 plus root 5 plus 1. All right, so remember squaring is actually when you have more than one term, you have to multiply your the whole thing, the whole term. So in this case, since it's a binomial, we have to multiply our binomials. Minus 4, 1 plus root 5 plus 1. All right. First term gets multiplied, second term gets multiplied. I'm intrigued since last time was the 0. Who knows? All right, so 1 times 1 is 1. 1 times root 5 is root 5. Root 5 times 1 is root 5, and root 5 times root 5 is root 25. Now distribute our 4. Negative 4 minus 4 root 5 plus 1. All right, let's simplify a little bit here. I don't want to forget my beginning. All right, so let's add our like terms. I have 3 terms that have root 5, so I'm going to add those together. So I have 1, 2, minus 4 is negative 2 root 5. Okay, it's not going to end up like the other one. And then the square root of 25 is 5 minus 4 plus 1. So I have some like terms here. These constants I'm going to put together. 1 plus 5 is 6. 6 minus 4 is 2. 2 plus 1 is 3. So just think about this, and I've been doing it each time, but the correct form in order to in which to write your term or your polynomial or whatever this is, binomial, is your constant first and then your radical on the end. So just keep that in mind. All right, that's our answer. Very nice. Okay, so I'm going to let you do B, and then we'll go over I and J together in our Zoom meeting. So if it's Friday, I hope you have a great weekend, and if it's Tuesday, I hope you've had a great weekend and you had a good you had a good 3-day weekend. All right, I'll see you in class.